So, in order, and it's again kind of the technical side of Introduction to Astronomy, but we do need to talk about, in general, kind of matter. And matter is made up of atoms. And I love atoms. So what we need to basically discuss are three particles. And physicists will tell you there's more than just three. That actually these three main particles we're going to talk about, and you might already be familiar with, are actually made up of even smaller particles. But let's just stick with protons, neutrons, and electrons. And I'll kind of tell you, for purposes of this course and your test, what you'll need to know about these things that make up atoms. And I'm just amazed. I love the concept of an atom. So atoms have kind of a crunchy center part called the nucleus. And a long time ago, actually, before we were trying to understand before we understood about the concept of a nucleus, there was an experiment that basically threw energy at a very thin foil of gold, and some of the energy came back, and that's because it hit the nucleus, and the other energy just kind of passed through in that, because actually it went through the blank space, the electron cloud that is actually outside of atoms that actually creates the volume of an atom. Okay, but anyway, so I think of nuclei as being kind of nice and crunchy. But the nucleus, there's two types of particles inside the nucleus, and so you may have heard of protons. Protons carry what we call a +1 charge. Every proton has a +1 charge. Also in the nucleus, is nice and hard and crunchy, are the neutrons, and the symbol for neutron actually has a little superscript 0. It's like Switzerland. It's not positively charged like a proton, and it's not negatively charged like an electron. Like Switzerland, it tries to kind of, actually, it's nice that it's there because it can help the protons kind of, what we say, coexist in the center or the nucleus of an atom. So that's kind of what we have going on. These, within the crunchy center, the nucleus, actually these two particles generally have mass. They have significant mass. Okay, whatever mass is, right? Okay, they have heft. So now before we leave the nucleus, I want to kind of point out that the protons, oh my gosh, I'll draw a little heart here, protons, because there's different, you know that atoms come in different flavors, different elements. Like one element is a hydrogen atom. One atom can be an iron atom. One atom can be a carbon, uranium, silicon, chlorine. Okay, those are all different elements. And they have this very similar structure we're talking about, but they differ by the number of protons in their nuclei. Okay, that's why this statement up here, that it's the number of protons that actually identify or are unique for a given element. So whenever you look at what's called a periodic table, where you have all these boxes that have little elements in them, you'll see the symbol for the element. So for instance, the symbol for carbon is C. Okay, then you'll see a whole number, and that actually is the number of protons in the nucleus of a carbon atom, all carbon atoms. Okay, it's amazing that atoms can be so similar, but yet have such different properties. Okay, so protons, neutrons, nucleus, they have mass. Well, outside the nucleus, we have, okay, and if it kind of looks like, oh my gosh, where is that electron? That's kind of one of the fundamental issues with electrons, is we can never really know where they are and how much energy they have both at the same time. So electrons are busy little subatomic particles. And actually, in an earlier chapter, we talked about energy associated with motion is called kinetic energy. So a lot of the energy that atoms have actually is associated with electrons. So electrons are in a cloud outside the nucleus. And the other thing about electrons is they are relatively massless. Now, they do have some mass, okay, but it's a fraction of an atomic mass unit compared to in the chewy center, the hard center, protons and neutrons have significant mass. One last thing before we leave this slide. The thing about electrons is they are susceptible to being actually in outer space, or here on Earth too. They may even want to leave, but electrons can actually be what we call ionized or removed from the atom. So here's the deal. And the number of protons are set, okay? But electrons can kind of go and come, actually. But as electrons go, can you see where if electron leaves, now we might have an imbalance in the number of protons, fewer electrons than protons. So actually that leaves what we call a charged particle. It's positively charged. Sometimes it's favorable for, just because of how the electrons are what we say configured, sometimes it's favorable for electrons to be dumped on an atom. And if that happens, actually we end up with a negatively charged. We have more electrons than protons, so it's a negatively charged ion. All right. So I mentioned the number of protons is unique for each element. So for carbon, it's six protons for every carbon atom. And we call that the atomic number is the number of protons in an element, in a given element. So the atomic number for carbon is 6. The atomic number for hydrogen, the simplest element, is 1. The atomic number for, I don't know them all, the atomic number for helium is 2. Every helium atom has 2 protons in its nucleus. The atomic number for iron, we'll be talking about iron in stars, but the atomic number for iron is 26. Every iron atom has 26 protons in its nucleus, okay, etc. So then we turn our attention to that chewy center, or that hard center, the nucleus. Remember I said that we have protons and neutrons in the nucleus. Now, the atomic mass number is a whole number, and literally, because it's a little bit different for some elements can have kind of different variations here with regard to mass number. But what you do is you investigate an atom of interest and you count protons, okay, which has got to be set in stone because it's unique for an element. And then you add to that the number of neutrons in that particular atom. Okay, so it's a whole number. It's an integer. So count protons, you count neutrons, and that's the what we call the atomic mass number, or mass number. So I'll kind of put up some examples here. Okay, we have hydrogen, helium, and carbon. Just kind of pointing out a few things I may have already mentioned, but with regard to their, with regard to their atomic number, this is the number of protons. Okay, hydrogen has 1 proton, helium has 2 protons, and carbon has 6 protons. That's its atomic number. Let's go ahead and go down to this row right here. Number of electrons. Now we're assuming that kind of the electrons are balancing out the protons. So actually, can you see in each of these cases, if we have 1 proton for hydrogen, we have 1 electron. If we have 2 protons for helium, we have 2 electrons if it's neutral. 6 protons for carbon, 6 electrons if it's neutral, okay? Now we get to this one right here, the atomic mass number, or the atomic number. Okay, atomic number of 2, 4, and 12. Let's pick on helium first, okay? All right. The mass number, or atomic mass number, that's the number of protons plus the number of neutrons. So if the number of protons has to be 2, do you see if we take 4 minus 2 is equal to 2 neutrons? Okay, that's how we got that 2 there. Let's look at carbon. Carbon, this particular carbon atom, they're telling us has a mass number of 12. If you take 12, which has got to be the counted protons plus neutrons, if you take 12, you minus the 6 protons, okay, and that must give you 6 neutrons. We good with that? So let's turn our attention to hydrogen over here. Now they're saying for this particular hydrogen atom, they have looked in the nucleus and they have counted a mass number of 1. Okay, a mass number of 1. So we take 1, so that's got to be the protons plus the neutrons. We take 1 mass number and we subtract the number of protons, 1 proton, okay? And notice that's why you see at the bottom here, there are no neutrons, okay? So that's how that works. So what we've been talking, because what I've already kind of alluded to is it's possible that the nuclei, the center of atoms, okay, that are the same element, like I'm showing down here, carbon. I have 3 carbon atoms, okay, so each of them, since they're carbon, needs to have 6 protons. It's possible that we have a different number of neutrons, Now, what that affects is not the atomic number, because the atomic number is going to be 6. Okay, notice that across the board, 6 protons. Okay, but what that affects, by the way, the mass number here is given in the upper left-hand corner, mass number of 12, mass number 13, mass number 14. What it, I don't say affects, but what it is telling us is that there must be, in the first case, we said that a mass number of 12 minus 6 protons for carbon, that means that there are 6 neutrons. We did that one before. Okay. Now, in this case, a mass number of 13, it's got one more particle in its nucleus than the carbon 12. And guess what that particle is? Another neutron. Okay, so if you actually take 13 minus 6 protons, that gives you 7 neutrons. The mass number 14 for carbon, you take 14, from that you subtract the 6 protons, that gives you 8 neutrons. See how that works? If you've ever heard of carbon-14 dating, we can do that, or scientists can do that, because actually carbon-14, that one form of carbon is relatively unstable. Okay? And living organisms incorporate carbon-14 into our tissues. When we die, no more carbon-14 gets added, and then basically to date us, last time we were breeding, they see how much carbon-14 is left. Kind of in a nutshell. Okay, so even though carbon, these different isotopes or isotopic forms of carbon would behave chemically the same, be integrated into our bodies, different tissues, okay, they have different properties with regard, or they weigh differently, okay, kind of from left to right. You would think carbon-14 would be heavier, and you'd be right. Okay, so we can actually use that to our advantage to test for these different isotopic forms. And their stability is a little bit different. Last but not least, and then we're kind of away from the whole atom thing, is to kind of just kick around this concept of a molecule. So molecule is made by 2 or more atoms that are have a chemical bond between them. So now as I'm holding up my fist, kind of picture my fist as being the centers of 2 atoms. Okay, so they're the nuclei, right? And what's outside the nucleus, right? It's electron cloud, electron cloud. So here's the deal. It's not just kind of a willy-nilly kind of, oh, gee, I think they should form a chemical bond sort of thing. It actually has to do with how the electrons would find it favorable, a mutually agreeable situation to go ahead and form a chemical bond. Okay, so there are rules about that, and it's about the electrons. What I think is so cool in astronomy is that we can actually see the signature for molecules in outer space. Fall 2014, for a long time now, we scientists have been looking for planets that are orbiting distant stars. And we're going to kind of talk briefly, how do they find those planets? You're like, really? Okay. But this fall, they have actually seen around one planet, they've got the signature for water. Isn't that not cool or what? So again, we kind of need to kind of consider atoms and molecules and electrons. You're going to see here in a minute when we talk about chemical spectra.